Hello everyone. Okay, so today we're going to be moving on to our last topic of this external, chemical reactivity. Okay, so these two are the learning intentions and success criteria for chemical reactivity. So have a look at these, and by the end of the topic, you should be able to tick off all these bullet points. So today we'll be focusing on the collision theory and rate of reaction. Okay, so before I go into collision theory, I do want you to watch this video. I have put this up on OLE, so have a look at that. Oops. Okay, so hopefully you've watched the video, but if you haven't, well, I guess that's okay. So this collision theory, it's about, what needs to happen for a reaction to occur. And it states that a reaction will only occur when the reactant particles collide, and that collision is effective or successful. And for the collision to be successful, the reactant particles need to collide. Oops, I'll move myself. Okay, they need to collide at the correct orientation, and they also need to collide with enough kinetic energy to overcome the activation energy. We will go over what activation energy is, so don't worry. So, if let's say, when we were doing our neutralization reaction, we mixed sodium hydroxide and hydrochloric acid together, right? And that led to neutralization reaction. Now, for that reaction to have happened, which it did, the hydrochloric acid particles and the sodium hydroxide particles had to collide, and those collisions had to be successful. And that means that hydrochloric acid and sodium hydroxide particles collided at the correct orientation, and they collided with enough kinetic energy so that they overcome the activation energy of the reaction. If they collided at the correct orientation but without enough kinetic energy, they will just simply bounce apart. And likewise, if they had enough kinetic energy but didn't collide at the correct orientation, the hydrochloric acid and sodium hydroxide particles would simply bounce apart. Okay, so let's go into activation energy. So this is probably a new term, so I'll go over it thoroughly. So activation energy is the minimum amount of energy that you need for a reaction to occur between two colliding reactant particles. So essentially, activation energy is the amount of energy you need to start a reaction. And you might ask, why do we need energy to start a reaction? Well, we need energy to break bonds between the reactant particles and also to form bonds in the products. So remember, we react hydrochloric acid and sodium hydroxide together to form water, sodium chloride, and you have to have broken, you have to break the bond between hydrogen ion and chloride ions. You also need to break the bond between sodium ion and hydroxide ions. And that way you form sodium chloride and water. And energy is required to do that. And again, if collisions happen without activation energy, particles will simply bounce apart and no reaction will occur. And you can see it in the animation here. So you can see that, so the blue circle and the square, they're reactant particles. Sometimes they'll bounce, sometimes they'll collide, but they don't really react. They'll just simply bounce apart. But sometimes they will collide with enough energy and at correct orientation, so they will react. Okay, so let's move on to reaction rate. The reaction rate is the speed at which a chemical reaction occurs. Some reactions occur rapidly, like when you add magnesium strip and acid, and you see that fizzing rapidly. Very quickly, and that's because the rate of reaction was very fast. Sometimes the reactions can be slow, like iron oxidizing or rusting. That happens slowly because the rate of reaction for that reaction is slow. Now we can measure reaction rate by observing how quickly the products are formed or change into products, or how quickly one of the reactants disappear. Might have to reword that actually. Reaction rate is measured by how quickly the products are produced or change. Okay, so how quickly the reactants change into products. Okay, and the shorter time it takes to react, the faster the rate of reaction. So that's nothing's too complicated so far. Okay, so let's have a look at this. I'm going to move myself. Okay, so reactions take place over time. And let's have a look at this example. So we have the pictures here with the reactant particles being purple and the product particles being green. And we also have this graph. So this purple graph represents the number of reactant particles over time, and the green graph represents the number of product particles over time. So at the start, we only have the reactant particles present. So you can see it here and in the graph. So we have 50 molecules of reactant particles and 0 molecules of products. But as the reaction proceeds, the reactants gets used up, so it decreases in number. But at the same time, the products are being formed. So as the number of reactant particles decreases, the number of product particles increases. And you can also see that in the picture. And at the end of the reaction, which is here, only the products are present because all the reactants have been used up. So we have 0 reactant molecules and 50 product molecules. But sometimes reactions might stop because one of the reactants have been used up. But in this example, we can say that both reactants have been used up. Okay, so now we're going to move on to factors of rate of reaction. This is a really fun video to watch. I've put it up on OLE, so do watch it. Okay, now I'm going to move myself again. Okay, so there are 4 factors that affect the rate of reaction, and you should know what they are if you have watched the video. The first one is the concentration of reactants. Second one is surface area of reactants. Third one is temperature. And fourth is a catalyst. I won't go into details about how these factors affect the rate of reaction, but tomorrow we'll discuss how the concentration and the surface area of reactants affect the rate of reaction. So that's all from me. I do have some Education Perfect tasks for you to do, so please get on to that. And yeah, thanks for listening.